You have fallen into Event Horizon with John Michael Godier. In today's episode, John is joined by Tory Bruno. Salvatore T. Tory Bruno is the President and Chief Executive Officer for United Launch Alliance. In this role, Bruno serves as the principal strategic leader of the organization and oversees all business management and operations. Prior to joining ULA, he served as the Vice President and General Manager of Lockheed Martin Strategic and Missile Defense Systems. He holds a bachelor's degree in mechanical engineering from the California Polytechnic State University in San Luis Obispo, California, and has completed graduate courses and management programs at Harvard University, Santa Clara University, the Y River Institute, San Jose State University, and the Defense Acquisition University. In addition, he is an American Institute of Aeronautics and Astronautics Fellow, a companion of the Naval Order of the United States, a member of the Navy League, and a former member of the Board of Directors of the Silicon Valley Leadership Group.
Tory Bruno, welcome to the program.
Thank you.
Now, Tory, ULA is originally the fusion of Lockheed and Boeing and their launch systems, which are illustrious launch systems. Atlas goes back to the very early days and before of the space age. And actually, as I recall, started as an ICBM and then was repurposed into a much, much longer lived system, a rocket system that's still around, even though the ICBM was only around for a few years. Can you tell us what brought about the fusion of the resources of Boeing and Lockheed to create a completely independent company, ULA?
Oh gosh, what a great question. Well, what brought that about was a looming crisis in space. So there were the confluence of two things occurring at pretty much the same time. The first was an over-facilitization and oversupply of launch vehicles in the commercial marketplace. It was anticipated that the internet was going to go to space, much like it is finally about to do with these LEO mega constellations. But back then, back in the 90s, late 90s, it was thought that would happen. And so the Delta IV was developed, Atlas V was brought forward, and the giant hockey stick increase in the launch market didn't materialize. And so both of these businesses were unhealthy and about to collapse, honestly. And that was terribly unfortunate for the country because at the same moment in time, the satellites that we have on orbit then were all reaching the end of their life. And in fact, we're extending beyond the end of their planned and design life, GPS, weather, communications, and their replacements were years late. There was, in fact, an expression in the government at the time that space was, quote, broken, because these new platforms were, in my opinion, very ambitious technologically and gotten a little bit ahead of themselves. And the programs were late. They were having technical problems. They were greatly overrun in many cases. And so here's this perfect storm. We're about to have our domestic launch industry collapse at just the moment we're trying desperately to avoid huge capability gaps in space. It was forecasted that there would be regions of the Earth with no GPS, that we were not going to have continuous coverage of weather, that communications were going to have big gaps in them. Our military forces would be out in important places in the world with no communications that were practical. It was a giant crisis. And so part of that answer was to ask Boeing and Lockheed to consolidate those two rocket platforms, to set up a standalone company, which is ULA, to inherit the two rockets, but then get it into one factory and one team and one set of launch operations and facilities so that it could survive basically on the government business that was present to try and avoid this crisis. And then never be late don't blow any up. Make sure you can fly whatever spacecraft happens to show up at the pad, because they're doing everything they can to get them there as quickly as possible. And they didn't always show up in the order they were expected, and try and minimize this big crisis that was going to happen. And in fact, we did all of that. We've never lost one. We're always on time. And we had the flexibility to launch whatever showed up. And all of this is probably new to many of your listeners because the crisis never happened.
Now, you mentioned the never losing a rocket and always being on time. Now, ULA has a truly stunning track record as far as launches and capabilities with both Atlas and Delta. And this in a business where things explode. It's the rocket business, yet you have this sort of reliability factor with ULA that has just been stunning. What do you attribute that to? What is it within ULA as a company that allows you to make these schedules and make these reliable rockets where sometimes others don't?
Well, I could go into a lot of details about how it's done, but the real answer is culture. I mean, it's as simple as that. Here, mission success comes first. It really does. It doesn't trump any other decision that I would ever make, that any of my people would make. I don't overrule them and say, oh, you're worrying too much about our financials, or you're worrying too much about our convenience. This is a mission success issue. That just doesn't even come up. It's in the water, if you will. And that means that we recognize that mission success is about our customer's mission, not ours. The rocket is amazing and we love our rockets, and a lot of us are in this business because we love that technology. But the rocket really isn't important. We're only there to carry somebody else's spacecraft into orbit. And we all know that and fundamentally understand it. And you can see it in small ways. So if you watch one of our live feeds from a launch, it's quiet in the control room all the way until the end. Nobody cheers at ignition. Nobody cheers at payload fairing separation, or second stage ignition, or any of these intermediate events, because there's nothing to cheer about until we have successfully separated the spacecraft and placed it in that precise orbit. Then everybody cuts loose.
Now, ULA is also known for precision in being able to put these things exactly where they need to be or where the customer wants. How do you do that? Because again, it's rockets and, things end up in incorrect orbits and all that, but ULA usually gets it right there. How do you do it?
Well, the precision itself is largely about the upper stage. All of it matters, and it is a system solution, but the upper stage obviously has the most profound impact and carrying that payload exactly to where it's going to go. And so everything about it matters. Our ability to terminate the thrust from the main engine exactly when we want to, our ability to control the attitude that is being done by a separate propulsion system when we're leading up to that or getting ready to separate, the separation systems themselves, the thermal systems. You might not imagine this, but just the thermal behavior of this giant rocket stage, even the upper stage, the tiny little upper stage, is still 40 feet long and 10 feet in diameter and filled with still, even near the end of flight, many, many, many gallons of these cryogenic propellants that are sort of sloshing around even in microgravity. So all of that as an integrated system is extraordinarily well understood, controlled, and modeled so that we know how to compensate for everything and then just precisely place that spacecraft. If you're familiar with us, and you are, John, you know that these are the most accurate orbital insertions in the world.
Absolutely. Now, I want to ask you this about autonomy within the rocket. Now, you can literally change according to weather conditions within a minute of launch. Now, how do you do that? What's that system look like?
Yeah, that's more about process than a piece of hardware. And that's another great question, because it's another unique thing about ULA. And in some respects, it has a little bit of heritage back to that ICBM history that you talk about on the Atlas. Whenever you're watching somebody's launch, you're seeing people let go of weather balloons. And what those are for are to go to fairly high altitudes to measure what we call winds aloft, jet stream often. And what everyone else is doing is checking to see if the winds aloft are greater than what they looked up in an almanac 6 months ago when they programmed the trajectory of the rocket. And if they're too high, then they might have to scrub. So it's really a safety check to see if conditions are consistent with forecast. And of course, what we're doing, as you alluded to, is something completely different. We're measuring the winds aloft, and then we're using that data to reprogram the rocket's trajectory right up, as you say, until just less than a minute before ignition. And it's really about a process. So we have, of course, designed our software to be what people will call parameterized. So in other words, you're not changing the logic a minute before launch, but you are changing constants in the software that define that trajectory. And so that's something that is built into technology, if you will. But really what makes it possible is our simulation lab in our trajectory analysis that's all the way back here in Denver. When we measure that wind aloft, that data goes into our winds team, and they understand what it means to the rocket. And then we develop new parameters, a new trajectory for the rocket in real time in our hardware-in-the-loop simulation lab, which is like an Atlas or a Delta rocket that is sitting in one of our buildings, all the electronics, all the sensors, just not the big propellant tanks, in a team standing by to pass that through a giant Monte Carlo simulation of many, many runs to make sure that that trajectory will work and nothing's going to go wrong. And then in real time, port it all the way out to Cape Canaveral or Vandenberg, depending on where we're launching from, dump it into the rocket, basically do a checksum to make sure it all got there, and then away we go. Nobody else does that.
Now, before we get into Vulcan and how the testing is being done for that system and what's going to launch first, before we get to that, now let's talk about legacies. We were talking about Atlas and the venerable old system that it is. And as a matter of fact, I think it was the second human-rated rocket past Redstone that we had. And what, through the evolution of Atlas to getting to Atlas V, what's left from that original rocket? Is there any legacy systems or anything left from the early days that are still put into the rocket that have proven so reliable that they're still in use?
Yeah, what another great question. So yeah, there's several things. And I'll say for your listeners, some of the easiest things to spot would be just looking at the rocket. You'll see this asymmetry when we add the solid rocket boosters to scale the rocket up for bigger or higher energy payloads. And I often get asked about that by space enthusiasts. Why is it asymmetric? Why can't you put a sixth? Because we can go up to 5. Why can't you put 6 SRBs on there? And you look at the side of it and you'll see a couple of things. You'll see an external pipe, feed line we call it, to bring the liquid oxygen down to the engine. But then there's also a lower profile run that's coming down the side of the rocket on the other side. And that is an aft avionics pod, which is where on the original Atlas SM-65 ICBM, all of the guidance systems were down in that pod because it really wasn't a multi-stage rocket. Not really. We shed engines, but we didn't stage and have completely separate stages like you see today. And that little piece of old-fashioned architecture continues right through to today. And it doesn't have, of course, the brains and the full guidance set anymore, but it has the electronics that control the flow of propellants and other things that are just unique to the first stage. So that has survived, how long is that? I mean, that's 40, 50 years now. So that little element has continued. The architecture of the software has similarities to all the way back, not just the SM-65 ICBM, but through Atlas, through all its generations, up through Atlas 3 and now to Atlas 5. So there are features like that, because in rocketry, we choose carefully where we want to innovate to get new capabilities and where we want to continue heritage to maintain reliability.
Where do we go from there now? So what parts, what aspects of Delta and what's going to go into Vulcan from previous iterations of the rockets?
Yeah, that's a great question, too. So, for example, we're maintaining the boosters' high-performance aluminum rigid structures that you see. If you see the inside of the tanks, this pattern is machined into them. On Atlas, we use what's called an iso grid. So they look like little triangles or little diamonds, depending on how you see them. And on Vulcan, you're going to see the same set of alloys and the same idea of a rigid tank with this pattern machined into it so that it's super lightweight and super strong at the same time. So that's carried forward, for example, but you'll see the pattern and the shape change to something we call an iso grid that is faster to manufacture and actually makes it a little bit lighter and a little bit stronger, taking advantage of modern analytical tools that allow us to analyze the stress more precisely than we could when Atlas V was designed. That's a feature. The architecture of what we call the dial rocket, being able to have 0, 2, 4, 6 solid rocket motors attached to the outside, that's a carry across. Innovations, it's a single core heavy. The single core Vulcan rocket has more lift capability than the 3-core Delta IV Heavy. That's the deliberate choice, and it collapses the price of heavy missions. And the Centaur V, which we can come back to later if you want. That's another big leap forward in technology and capability, while much of the rest of the rocket is brought forward. We developed new avionics for Delta IV and Atlas a few years ago. Those are coming forward onto Vulcan. There's no reason to change them. We like the dialer rocket, that comes forward. Where we've made changes, we have made them in a way, in many cases, that they are compatible with Atlas, so we can fly them before Vulcan flies. And then those will roll forward. For example, we're already flying not just the avionics, but the SRMs. The difference between an Atlas SRM today and a Vulcan SRM is just the length. It's the same rocket motor. We've already done that. We've improved the fairing for Vulcan, but we've started flying it on Atlas. So that by the time we get to Atlas's first flight, the only thing that is entirely uniquely new will be the first stage rocket engine, because that's the one thing you can't fly unless you fly it.
Now, this is basically testing the rocket in pieces before you actually fly an actual rocket. Now, this is interesting because you're not going to launch a piece of concrete. You're not going to launch a test or anything like that. You're actually going to do a mission with the first full launch of Vulcan. Can you give us an overview of that?
Yeah, we are, and we're super excited about it. We will be taking the first commercial lunar lander to the moon for a company called Astrobotic, their Peregrine Lander. And it's a lander that can carry different missions. And it's pretty exciting for us because not only is it, as you say, a real mission, not just a test flight, but it's a pretty cool mission for your first launch to go to the moon and then do a first at the moon, which is this commercial lander. We think that's pretty awesome. And I'll share something with you that a lot of people don't know, but you could buy tiny little payload bays on this lunar lander. And early on, when we were going to fly that mission, I just couldn't resist. So we have bought a tiny little payload bay that will contain the names of all of the ULA employees at the time. So I can say that I'm sending all of my employees, my entire workforce, to the moon.
Very nice. Now, this is a beast of a rocket, Vulcan, and it's not just the moon. We, of course, Mars and all this, but how does this shrink the solar system? I mean, with a rocket of this capability and this launch liftability, how does this change how we do missions? I mean, would you do something like the Parker Solar Probe a little bit differently with this capability than what was there at the time? So how does this change that landscape?
Yeah, that's another great question. So I'll say in a rather straightforward way, and then in a way that's a little bit more subtle and more exciting. So the straightforward way is simply that it is a beast of a rocket. And so that means that you can either launch larger payloads to places like that, or you can have larger windows so that you're more likely to be able to launch when you need to. And that's important when we talk about the solar system, because interplanetary missions typically have a window of time. when you can go. And if you miss it, there might be a long period of time before you can go again. Obviously, going to Mars, that comes around every 26 months because we literally have to wait until the planets are aligned, until we are coming up and about to pass Mars, and we can launch on a trajectory out to Mars. And if you miss that window, and it's typically only a couple months long, the next thing you know, you're on the other side of the sun. And so you're going to wait 2 years before you can try again. That's not too bad. We're going to fly a mission called Lucy out to the Trojans that precede and follow Jupiter in its orbit. And a really cool mission, 9 objects that we're going to go out and study that are going to reveal things about the early formation of the solar system that is literally once in a millennia mission. If you don't make that window, you can't hit those objects ever again in any human span of time. Pluto was another one. I mean, every 200 years, a mission like New Horizons. So that part matters, even though it's kind of straightforward and maybe a little bit mundane. It's just about having a bigger rocket. But then there's something else. There's the upper stage. And we are continuing the technology of Centaur, but the Centaur 5 that will fly on Vulcan is more than 2.5 times the energy, and it will have initially 40% more endurance on orbit, and then that increases. We already have technology in work so that we'll go from a Mark 1 to a Mark 2 to a Mark 3, greatly extending the life of this thing. And once that giant first stage has taken you out of Earth's gravity well and got you to orbital velocity or very near to it, it's all about the upper stage. And the capabilities on the upper stage allow us to really make the solar system so much smaller, to make it more practical to go to the outer planets, to do more complicated missions to and from the moon, and to really begin to basically change the paradigm of how we operate first in cislunar space and then beyond. So watch the upper stage. That's the really exciting thing about Vulcan.
One question about that, particularly the upper stage and other aspects of the rocket, the engines and things like that. Smart reusability. Now, reusability has been a thing that we've all been watching in the rocket industry for some years now, some to stunning results. And now ULA is looking into eventually pursuing that with Vulcan. What's that going to look like? What parts are you going to reuse, and what parts just aren't worth it?
Yeah, we're going to start with 2 elements. And the first one will be something you get to see, and that'll be component reuse on the booster. We're going to separate our engine section and recover that, and that's what we call smart reuse. And it makes a lot of sense for us because we really specialize in the high energy missions, the missions that are hardest to achieve. And we like this technique because it doesn't really have a significant performance impact. When you want to bring your entire booster back propulsively and land it, you have to save a lot of propellant to fly back home with. And in terms of your maximum capability for any given orbit, and by the way, payloads aren't always at your rocket's maximum, and that's why this can make sense for some people in certain situations. But in terms of that maximum, it'll cost you 30 to 50% of the mass of the payload that you could ultimately take to space if you're saving all this propellant to fly your booster back home with. And for us, because we specialize in the high energy stuff, that didn't make a lot of sense to us, for us, and it wasn't very attractive. So instead, we're going to cut off the engines, re-enter those behind this really cool inflatable re-entry shield that we're developing together with NASA for a future Mars mission, and then parachute them down and recover the engines that way. The downside is you don't get the whole value of the booster back. You've only gotten the engines back, but the engines are about 2/3 the cost of a booster, because once you separate that engine, what have you got? Well, the rest of it is just an empty gas tank. And so that's why that made sense for us. The other thing is the upper stage. The capability in terms of how much energy Centaur 5 will have, and this increase in endurance means that it can do more than one mission when it goes to space. It essentially becomes a reusable upper stage in space. So sadly, you won't see them fly back. They won't land. They won't come back under parachutes. Nothing like that, because we're not going to give up the investment we just made in their orbital velocity, but they are going to be out there doing multiple missions and really fundamentally changing what you can do in Earth orbit and especially in cislunar space. So a little bit different strategy. The booster's about economics and making that just more affordable and less expensive by reusing pieces of hardware. The upper stage is going to be about whole new missions. Now, in terms of what doesn't make sense, which was part of your question, I explained a little bit about why we'd rather do engines rather than the propulsive flyback. But in addition to that, there's lots of other components. We could do other components if we wanted to. We took a real hard look at the payload fairings, and we're at one time actually on a track to be serious about recovering payload fairings. But our strategic partner, Ruag Space, who's doing the new payload fairing for Vulcan and also flying it first on Atlas, as we talked about, because of the things they were able to do with their manufacturing processes, advanced technology, the price of that thing cut in half. And then it became really hard to close a business case on recovering it. Because when you recover pieces of a rocket, you're always starting with an expendable rocket. And then you're adding things to it and adding operations that allow it to be recovered and refurbished and reused. And those things cost money. And so you have to use it a certain number of times to recover that cost and then start saving. And when the item itself gets less and less and less expensive, perversely, it's harder and harder to actually save money by recovering it and reusing it. So the payload fairing got set aside. There were other elements like that. Avionics are another thing we think about, but are set aside for the moment. And so our economically focused strategy on reuse is to start with the engines, where we know we can save money, and then see where that takes us as we learn how to do this.
Reusing the upper stage in space. Now, what's the game plan there? I mean, are you going to manufacture propellant up in space and refuel these things for other uses? And what uses could we get out of it? I mean, what's an example?
You want to think of this as a journey. So we start with extreme duration and propellants that we lift from the Earth and doing more than one mission, maybe even many missions in space. That's where we're going to begin. Ultimately, on the other side of this, I have a vision for what is going to happen in cislunar space that is entirely enabled by the thing you touched on, the presence of water on the moon. And as I think you probably appreciate, water isn't just something that humans need a lot of wherever they are, including space. It's also rocket fuel. It's pretty easy to break down water into liquid oxygen, liquid hydrogen. So fortunately, it's not even a difficult process. And fortunately, these are the most energetic chemical propellants that are in practical use. And then the final, key to this unlocking the cislunar economy that I talk about often is the fact that it's already in space in enormous quantities. And the moon, we now believe, has well in excess of 20 billion metric tons of ice. It is, in an inconceivable span of human time to consume all of that in terms of propellant, even at the levels of consumption that I imagine for a cislunar economy that will spring up as a result. We're talking a million years of propellant. We'll be well beyond the moon. We're not going to run out. We'll be out to the outer planets and other moons by the time we get even anywhere approaching something like that. And because of the tremendous natural resources that are present on the moon, and especially on the near-Earth objects or asteroids that are within reach of the moon, just beyond it, having that propellant in space so that we don't have to lift it all out of the extremely deep gravity well of the Earth enables that in situ utilization of propellant that unlocks all of that. We're talking about a thriving economy in space where we're harvesting these natural resources, we're bringing them back to the Earth. All the things that are scarce here are not scarce there. They're only scarce on Earth because of the way our planet formed. And then eventually using them in industrial applications in space itself. We're talking about a post-scarcity human future.
In space and using comparatively limitless resources of space, and the fact that you can mine things like iridium that we don't really have very much of down here on Earth, but we have plenty in the asteroids. So this gives us basically a human future in space, and we can build things from that, manufacturing in space. And that may actually end up being easier than manufacturing here on Earth, right?
Absolutely. You've got it.
Now, ULA and the moon. Now, we talked about the lander. That's going to be the Peregrine Lander. Now, what else? What other customers do you have coming in to support the human return to the moon, Artemis?
Several. And so we're very focused on the first missions of Artemis and sort of the public consciousness, which is great. And that's the establishment of the Gateway Space Station, essentially an ISS that orbits the moon, and it will be a permanent research platform, and people will be permanently on station there doing things. And then, of course, the most exciting part, putting boots in the regolith once again. And NASA is off competing human landing systems and making awards, and people are off to go do that. And that's all very exciting. We were on one of the teams that sadly was not selected for the human lander, but to support all of this future activity, there is a tremendous logistics operation that follows. There are a couple of reusable elements to the human part of the mission on the surface of the moon, the descending to the moon and returning. But a lot of this material is consumable. Lots and lots of propellant and food and water and people going back and forth and new pieces of equipment being brought up to replace the equipment that stays on the moon or eventually wears out. And of course, the equipment and activities that will begin not just the research for where all the wonderful minerals and water is, but actually processing that water into propellant. That is a gigantic ongoing activity that will dwarf the initial bringing of people to the moon to start all this and then back home again. We intend to be a part of all of that. And Vulcan and the Centaur 5 help to enable it. One of the neat things about endurance, because I talked about that as one of the new technologies in Centaur 5, is taking the very long endurance of Centaur 3 and really extending it out many, many, many times, is the ability to make logistics trains that are ongoing more efficient. We like to use, all of us, when we go to space, things like Hohmann transfers and translunar injections, and those are great, relatively prompt paths that are pretty economical in terms of the use of propellant and the energy they use. But if you had a lot more endurance, you could add trajectories like the weak stability boundary trajectory, which can, depending on where you're going and how you do it, increase your payloads by as much as 25, 30, even 40%. They just take a lot longer. Well, if it's a continuous train of material going back and forth, the time to get there isn't as important as the amount of payload you can deliver in each increment. So that's another thing that Centaur 5 enables, that regular, efficient logistics train just going constantly out to the moon.
Now, on to Mars. How many times has ULA launched to Mars?
Yeah, we've taken 20 missions to Mars. And so that was one of our little jokes inside when we flew Perseverance. You recall that mission was originally called Mars 2020, and we called it Mars 2020 because it was going to be our 20th mission. We've done all U.S. missions to Mars up to this point in time. So we got a lot of experience going there.
What's the future for ULA and Mars?
We're going to keep doing it. I think there'll be other people going to Mars, and I think that's a good thing because we want to start doing a lot more research at Mars in preparation for human exploration. And a broader industrial base can only support that. So we'll want to continue doing, I'll say, what we're good at, which are the most complicated, most critical, most time-sensitive kind of missions out to Mars. But I fully expect there will be other people going there as well. The other thing I would want people to understand about human exploration of Mars is that the moon really is on the way there. And I don't mean literally like you fly to the moon and then you fly to Mars. What I do mean is there's a lot of research that has to be done and technology that has to be developed in order to make a human presence on Mars practical and safe. There are a number of issues because of the duration one is in space for a Mars mission that are different than what we experience on the International Space Station. For example, on ISS, you're inside the Earth's magnetosphere, and although much higher than the radiation levels you experience here on the surface, still pretty manageable. But when we go to Mars, we're on the outside of that magnetosphere, and we're experiencing an order of magnitude greater intensity, and for a very long period of time. You really can't do a Mars mission in less than 2 years, including the time you were on the surface as well as the transit. And because of that duration of time and the fact that we want this to be routine travel back and forth, the odds of encountering a solar proton storm really go up. Sooner or later, you're going to be in the path of one of these. And if your viewers are not familiar with that, the way to think of it is that periodically our sun just blasts a giant death ray out into space. And if you're in front of it, it is absolutely lethal if you are not properly protected and shielded. We've had close calls through Apollo, where astronauts have been literally within a few months of having been in the way of one that would certainly have been injurious, if not caused death. So that sort of thing has to be well understood, along with all the other health impacts like long-term exposure to microgravity and so on. Where's the right place to do that? It's at the moon. The moon's never more than a few days away. We can routinely go back and forth. We can do research. We can gradually walk our way up in terms of how long people are exposed to these environments as we make it safer and safer and we understand it better until we're ready to have routine travel to and from Mars. So don't forget the moon when you think about people on Mars.
Now, this seems to create sort of a real issue for a rocket scientist because with those levels of radiation, you need shielding. And we can't be launching lead into out of Earth's gravity well. We need to do something better. So what are some alternatives that we could do on, say, the moon? I mean, can we melt some of that water and make a lunar concrete? I mean, can we do certain mitigating things that make the radiation not so much of a problem while also not having to tackle it with rockets?
Yeah, absolutely. And your instincts are really right on, John. You know, one of the better materials for radiation shielding it is in fact water because of its hydrogen content. And so it can be water, it can be regolith, you can go underground. All of that is practical on the moon for in situ facilities. They're not practical necessarily for long distance interplanetary travel. Water's pretty heavy. And of course, as you alluded to, our other favored materials, lead, concrete, are not common materials in the design of spacecraft. So, but the key is the hydrogen. And so there's an opportunity here to develop materials that mimic that behavior and contain that particular element, potentially, to achieve the same kind of radiation shielding for much less volume and much less weight, so that the transit through space becomes a lot more practical. But yeah, on the lunar surface, we can absolutely and will absolutely need to move to using those in situ resources to build the facilities and the shelters if we're going to do that at any scale.
So we end up with regular science missions, manned science missions to Mars. What is the end game? People had always talked for many years about terraforming Mars. Now this is looking a little bit questionable. And I've seen your Twitter. You sort of said, well, give us your views on terraforming Mars.
Yeah. So I'll come back to colonizing Mars, but yeah, we'll start with terraforming. Not going to happen. It was something we thought was possible a handful of years ago because we thought that there was a lot more CO2 on Mars than there is. And it was imagined that if you had a way of liberating that and having it captured by Mars gravity into an atmosphere, that we could start a cycle where we begin to warm the planet and potentially even have, liquid water on the surface. And it's still, even then, a little bit science fiction, but over very long time scales, perhaps it could have been terraformed. That was the idea. And then some of those 20 missions that we took to Mars did some much more accurate surveys of what was present there, especially in the caps, and found out, no, there are many orders magnitude less of that particular constituent than we originally had hoped would be there. And the simple fact is, there just isn't enough. And you're not going to be able to terraform Mars. You would have to bring the CO2 from somewhere else. And when we talk about the quantities and where it would come from, well, we could divert comets. We could divert hundreds of thousands of comets to impact on the surface of Mars. Forget about we'll just set aside any ideas around planetary protection or, the conservation ideas about doing something. We'll just set that aside and we'll just stick with the physics for a minute. We don't have the technology to do that over any human time scale. And, by the time we could divert, 100,000 comets or, 1 million comets to impact specifically on the surface of Mars of the right kind, maybe we'll just also be able to go to an exoplanet that's already Earth-like. Terraforming of Mars is not happening. There's general scientific consensus on that. Doesn't mean there can't be a Mars colony, a permanent human presence on Mars that goes beyond just a research facility. But it does mean that it's going to be living in a shelter, and it will absolutely be dependent on trade and exchange with Earth, because there will be things you can't make on Mars or have on Mars that are required without Mars being an Earth-like planet. And that's not terrible. Throughout human history, there have been plenty of colonies that were dependent upon Europe or dependent upon, for example, Iceland and Greenland was a chain into the initial Norse presence in North America. That globalization is something we understand today. So you don't have to be entirely self-sufficient. You just have to have the means to live there. You have to have a certain amount of self-sufficiency. And by the way, you have to have the means of trade. If all we're doing is putting people underground on Mars or in a shelter on the surface of Mars and sending every single resource they need or consume, we haven't done very much. It would probably be better to invest that at the moon. It would be really no different. Or to invest it in making Earth healthier and safer and better maintained. What we would really want is for the people who are on Mars to be producing and generating things that they are trading with Earth in order to obtain the few things that they lack to be able to live there.
Specifically with the moon, that sort of trade is definitely on the table, especially when you start talking about fusion and helium-3 and things like that. The moon has something to offer. Does Mars have any immediate thing that would be of value to return to Earth?
Well, that's the thing that the research mission will discover when we can actually put people on the surface of Mars and understand it so much better. We'll have a much better idea of what might be there that is rare back here on Earth that's worth trading for.
Now, my last set of questions for you is about you. Now, how did you end up as a rocket scientist? At what age did you say, that's what I want to do?
Okay. Well, believe it or not, I was about 8 years old. I was I was a little boy growing up on a small ranch in California up in the mountains near Lake Tahoe. And I saw the first man, not the movie, but, Neil Armstrong walking on the moon on a black and white TV and was absolutely captivated by the idea of space from that point forward. And just a few months later, I was building my own rockets out of some moldy 80-year-old dynamite I found in the back of my grandmother's barn, and cutting open these sticks and pulling out the powder and the diatomaceous earth and packing that stuff into some wrought iron pipe that I also found in the barn, and launching rockets. And a few of them actually got a little ways into the sky before they detonated. And and today you'd probably get arrested. I mean, I didn't know it, but I was really making pipe bombs, but I was trying to make rockets. And that's when I decided I wanted to be a rocket scientist. And, it was a little bitty ranch, so we didn't have a lot of money. We were respectable folks, but we didn't have a lot of money. So I saved up money until I could afford to go down to Cal Poly and go to engineering school and then go off into the industry, and have had just a wonderful career ever since. But yeah, it started with what inspired so many people to want to be interested in space.
Now, we'll get to inspiration in a second, but would you, Tory Bruno, CEO of ULA, would you go to space?
Yeah, absolutely. Just don't tell Mrs. Bruno.
I think that probably works for everybody that goes to space. Now, my last question for you deals specifically with inspiration, and specifically with the Parker Solar Probe, which was a stunning launch and a very harrowing way to position a spacecraft to explore the sun. And you had told a story about Dr. Parker. Could you recount that here?
Certainly. I often get asked, what was your favorite mission, or what's your favorite rocket? And I always say, well, I love all my children, and I do. But I have to admit, Parker Solar Probe really has a special place for me because of Dr. Parker. He was a rebel. When he first theorized the presence of solar wind and this notion that the empty vacuum of space wasn't really empty at all, and it was filled with material and filled with energetic particles, people thought he was a crackpot. And he had to stick by his guns and be convicted of what he knew to be true. And eventually, he was proven correct, and his theories are accepted. But for that launch, that lifetime of scientific achievement and understanding of our fundamental driving force in this solar system, our sun, came all at once to a single point in this probe that would go up and complete that life's work and just fundamentally add to our understanding of the sun and the solar environment in the journey he had been through. And here was Dr. Parker still with us, fortunately, to see his gigantic 30-story high rocket with this spacecraft on top that would become the fastest human object in the universe. It was touching. And to be there with him and to see, his emotional response to all of that, and to be a part of that complete story, it's hard to describe what that feels like. And it's one of the things that make it so amazing to work in the space industry, is to be able to be involved in things like that. So yeah, that one's my favorite. And, when we start out on a mission like that, there's a lot going on, and I'm downstairs on console and everything. But at the right time, I ran upstairs so I could be with him out on the roof for that launch, and have our hands on the rail, and have that rail, have it vibrate and have the sound be deafeningly loud. And it's just, all the things that go with a rocket launch. And to be there and do that with him was really something special.
That's absolutely amazing. We are out of time. I want to thank you, and I want to wish good luck to you and everybody at ULA on the Vulcan Centaur rocket system. And I really look forward to that first launch. That's going to be amazing to watch.
Well, thank you, John. I'm pretty excited about it too.
Thanks for listening. I am futurist and science fiction author.
Wrong channel.
No, it's not. Thanks for listening. I am futurist and science fiction author John Michael Godier, currently hosting Event Horizon and wondering where Anna actually came from. One day I had a tablet computer, the next I had a boss. Very disturbing, and be sure...
And that's enough of that.
YouTuber forever! Like, subscribe, and hit the bell!
Sell out.
What?